Think about all the essential technologies that help our society to function, especially our modern society. From the integrated circuit to the modern tools we use to communicate, and even the infrastructure that sustains our internet. So all these things have one thing in common. They're built around high-performance semiconductors. Unfortunately, 5 billion people around the world don't have access to these technologies because, next slide. High-performance semiconductors like silicon are very expensive to manufacture. They require specialized facilities, and ultimately they're monopolized by a few countries. And so the question is, can we grow high-performance semiconductors at room temperature and conditions that are very similar to a high school chemistry lab, using tools that are no different than what you would find in a kitchen? Because if we could do that, then we've lowered the cost immensely of all the technologies related to semiconductors, and we've also lowered the entry barrier for developing countries like Saudi Arabia to develop their industries around high technology so they can catch up with developing nations. So we started looking at a different kind of material than silicon, a material called hyperperovskites. And this is a material that people knew about 70 years ago, but they couldn't grow into a high-performance semiconductor. And we reasoned that if we grew it with a very low amount of defects, we could turn it into a high-performance semiconductor. So we took a very simple approach. We stored the material inside a good solvent, and then we kept it inside a chamber containing a bad solvent. And over a matter of 8 days, a crystal grows. Next slide. And we were surprised when we measured the properties of the crystal. We found that it is identical, or even better than, the highest quality grade optoelectronic silicon that you could make at very high temperatures. So we made something at room temperature that's equivalent to something that was prepared in a very specialized fab at 1400 degrees Celsius. Next slide. Recently, we discovered that we could actually accelerate this process to happen within a matter of minutes. Next slide. So the crystals we grow and are the kind of disruptive materials that we developed at KAUST, just a few miles from here. And these are my students, and this is my lab. And we develop materials that will change the frontier of semiconductor applications. Thank you.